Okay guys, this will be a very short video. I didn't realize that I only had two more slides to do in topic 1A, so I'm just going to quickly go through Dalton's law. Dalton's law is for gaseous mixtures, perfect gas mixtures in fact, and what it states is that the total pressure of a perfect gas mixture is just a sum of independent partial pressures. So here we have the pressure of a gas mixture, the total pressure, is expressed as the sum over gas components, and Pi is the partial pressure of the ith gas component. If you plug in the perfect gas law for each gas component, you can factor out R times T over V, and this gives you just a sum over the number of moles of each gas component, which you can write as simply in total times R times T over V. The partial pressure of each gas component just obeys its own ideal gas law, and then here we've stated that the total number of moles is just simply the sum of the number of moles of each gas component. We will also introduce here a quantity called the mole fraction, which is a concentration unit. It's unitless, and the mole fraction is frequently used for gaseous mixtures. So you take the number of moles of component I and divide it by the total number of moles of gas that you have. If you make various substitutions, you can also write the mole fraction in terms of the partial pressure of the ith gas component divided by the total pressure of the gas. And so taking this second equality, you can rearrange it, and this gives you an alternate method for calculating the partial pressure of a gas component. As long as you know the mole fraction of that component and the total pressure, you can calculate the partial pressure in this way. So you can either calculate it in this fashion, or you can calculate it this way. Okay, so we're going to do a little practice problem here involving gases. They tell us that the mass percentage, the mass composition of dry air at sea level is approximately 75.5% nitrogen, 23.2% oxygen, and 1.3% argon. What is the partial pressure of each component when the total pressure is 120 atms? So let's assume that we have simply 100 grams of gas. Okay, so we'll just assume that we have 100 grams of gas, and that means that we have then 75.5 grams of nitrogen. We're going to convert that to moles, so we'll divide by 28. We'll just call it 28 grams per mole. That'll give us the moles of nitrogen. We'll do the same thing for the O2. We'll take the 23.2 grams of O2 and divide by its molar mass. And we'll do the same thing for argon. 1.3 grams of argon. And unfortunately, I don't remember argon's molar mass off the top of my head, so we're going to have to quickly look that up. $39.95. And so we'll get these done real quick. 2.7 moles. I'm getting 0.73 moles. And 0.33 moles. Okay, so we've got the number of moles of each component. we can add up and get the total number of moles. I'm getting 3.76. You know, I made an error here. I forgot a 0. I thought that looked a little too big. 033. Let me check the oxygen just to make sure. I think that one's right, actually. Yeah. So that number's not right. Let me correct this. 2.7 plus 0.73 plus 0.033. So that's giving me 3.46 moles. And so there's our total. And so now we can calculate the mole fraction of each component, and then we can use the expression Pi equals the mole fraction times the total pressure, like so. So we'll do the partial pressure of the N2. That's going to be 2.7 divided by 3.46 times the 1.20 ATMs. And so I'm getting a partial pressure of 0.93 ATMs. I guess I should round up. 94 ATMs. All right. So the other ones are identical to that, and I'm going to simply leave those as an exercise for you. For the oxygen, you would take the number of moles of oxygen, divide by the total, multiply by 1.2. For the argon, you would take the moles of argon, divide by the total, and then multiply by the 1.2. So each calculation will be the same as the one that I've just done. So I'll just let you guys take care of that one. And I'm going to go ahead and stop this video here.